day everyone. So we are the group 2. So we are about to present the data structures and algorithm in week 10. So the 3 data structure AVL 3. So the AVL 3 and the materials. So the AVL 3. First, identify whether an AVL 3 is balanced or not. Second, use rotations to balance an imbalanced AVL. Last, be able to search, insert, and delete a node in the AVL implement in Java code. So the materials are computer, student, activity sheet, and the cell phone. So this is our references. So let's have some review. What is a binary search tree? A binary search tree, also called an ordered or sorted binary tree, is a rooted binary tree data structure whose internal nodes each store a key greater than all the keys in the node's left subtree and less than those in its right subtree. It is used in computing. Binary trees are mainly used for searching and sorting as they provide a means to store data. Second question is, when is a binary search tree appropriate? Implementing a binary search tree is useful in any situation where the elements can be compared in a less than or greater than manner. For our example, we use alphabetical order as our criteria for whether an element is greater than or less than another element. So by presentation, named after their inventor, Adelson, Velsky, and Landis, AVL trees are height balancing binary search tree. AVL tree checks the height of the left and the right subtrees, assures that difference is not more than 1. This difference is called the balance factor. So here we see that the first tree is balanced and the next 2 trees are not balanced. So in the second tree, the left subtree of C height 2 and the right subtree has height 0. So the difference is 2. The third tree, the right subtree of A has height 2 and the left is missing. So it is 0. And the difference is 2 again. AVL 3 permits difference balance factors to be only 1. So but the balance factor equals height, left minus subtree minus height, right minus subtree equals negative 1, 0, and 1. So if the difference in the height of left and the right subtrees is more than 1, the tree is balanced using some rotation techniques. Take note, the right subtree should always be greater than the left subtree. If node is equals plus 2, then it is heavy on the left side. If node is negative 2, it is heavy on the right side.
AVL rotations: left rotation, right rotation, left-right rotation, right-left rotation. The first 2 rotations are single rotations and the next 2 rotations are double rotations. To have an unbalanced tree, we at least need a tree of height 2. With this simple tree, let's understand them one by one. Left rotation. If a tree becomes unbalanced when a node is inserted into the right subtree of the right subtree, then we perform a single left rotation. In our example, a node A has become unbalanced as a node is inserted in the right subtree of A's right subtree. We perform the left rotation by making a left subtree of B. Right rotation. AVL tree may become unbalanced if a node is inserted in the left subtree of the left subtree. The tree needs a right rotation. As depicted, the unbalanced node becomes the right child of its left child by performing a right rotation.
Now going to create our own AVL tree. So follow the order of the data to start the root node of the tree. Next step is to operate rotations whenever there is an imbalance in the AVL tree until you finish all the data and balance every node in the AVL tree. So if there is no imbalance, then we are not going to perform or operate rotations. We are just going to input them directly. So we are going to perform now or create now our own AVL tree given the root node of 14, since This is the starting data. Next is 17. 17 is greater than 14, so we're going to put it on the right. Next is 11. 11 is less than 14, so left. 7 is less than 14, less than 11, so we're going to also put it on left.
Next is 53. 53 is greater than 17.
Greater than 14, greater than 17, so we're going to put it here. And then next is 4. So 4 is less than 14, less than 11, less than 7. So we have an imbalance in the left part, left child of the left sub 3. So we're going to operate a right rotation. So we need to tilt this or rotate this, making the 7 now the left child. 11 is the right sub 3 of the left child. 4 is the left sub 3 of the left child. So on the next 3 now we are adding 13 and 12. Same principle on how would you insert this. So we're going to insert it here and here. So and the imbalance occur on the right child's left sub 3. So we are going to operate right left rotation.
And now, in continuation of the AVL types of rotation, let's go to the left-right rotation. This rotation is a double rotations or slightly complex version of already explained versions of rotations. To understand them better, we should take note each action performed while rotation. Now let's first check how to perform left-right rotation. And did you know that a left-right rotation is a combination of a left rotation followed by the right rotation? Now let's go to this image. In this image, a node B has been inserted into the right subtree of A and the left subtree of C, because which the C has become an unbalanced node having balance factor of 2. And now let's go to the second image. In this image, we first perform the left rotation on the left subtree of C. This makes A the left subtree of B. And now to the third image, it shows that the node C is still unbalanced. However, now it is because of the left subtree of the left subtree. I mean, because of the left subtree. And to the in the next image it shows that we shall now rotate the tree, making B the new root node of this subtree. C now becomes the right subtree of its own left subtree. And now for last, this image shows that the tree is now balanced. Now let's go to the right left rotation. And the second type of double rotation is a right left rotation. Did you know that it is a combination of right rotation followed by left rotation? And now in the right left rotation, this image shows that a node has been inserted into the left subtree of the right subtree. This makes A an unbalanced node with a balance factor of 2. And the second image is, first we perform the right rotation along C node, making C the right subtree of its own left subtree B. Now B becomes the right subtree of A. And the third image shows that node A is still unbalanced because of the right subtree of its right subtree and requires of a left rotation. And for the next image, it shows that a left rotation is performed by making B the new root node of the subtree and A becomes the left subtree of its the right subtree of B. And for the last step is where this images is the tree is now balanced. And the topics to be continued.
So, on the next part, we're going to identify where the imbalance occurs, and from that, we can identify what rotation to use. In the illustration above, we are given a tree which is imbalanced as balance factor 30 is equal to positive 2. So we can understand that a single right rotation is performed here, since this type of rotation is identified when a node has a balance factor as positive 2 and its left child has a balance factor as positive 1. We're going to rotate the node 20 as followed by the arrow. So here we have followed the single right rotation, making 20 the root node. On the left child, 10 is already the left child. The tree is already balanced because the balance factor is now 0. We can see that the left child tree, which is 10, is less than the right child tree, which is 30. Now we can remember that the note which stated above is that the left child tree should be less than right child tree. So now the tree is balanced. On the second illustration, we're going to use left rotation since it is RR imbalance or right-right imbalance, meaning that the imbalance occur on the right child's right subtree. Here is the illustration above. We can understand that the balance factor is equal to negative 2. A single left rotation is performed in this tree. This type of rotation is identified when a node has a balance factor as negative 2 and its right child has a balance factor as 1. So we are just going to follow the arrow, making 20 the root node. On the next part, after the single left rotation is performed, 20 is now the root node, while 10 is the left child and 30 is the right child. Now we are done with the single rotations. Now we are going to proceed on the double rotations and how to use it. So double rotation, right-left rotation is used when there is a right-left imbalance in your AVL tree. This rotation is performed when a node has a balance factor as negative 2 and its right child has a balance factor as positive 1. So we are going to perform a right and left rotation of an imbalanced tree as balance factor 10 is equal to negative 2. So next, performing a right rotation at node 20 and a left rotation at node 30. So we're going to follow the arrow. So first, we will perform a right rotation at 20 here. See? After which, we're going to perform a left rotation at node 30. Next, after right-left rotation, the root node now is 20 and the left node is 10. Right node is 30, making the balance factor in all three equal to 0. Now, the tree is balanced. Now, on the last illustration, we have a left-right imbalance. This imbalance occurs when a node has a balance factor as positive 2 and its left child has balance factor as negative 1. So if we are going to have a left-right imbalance, meaning to say that an error occurs on the left child's right subtree, we are going to perform left-right rotation. So in this illustration, we are given a tree, an AVL tree, which is imbalanced as balance factor 30 is equal to negative 2. So we're going to perform a left rotation at node 20 and a right rotation at node 10, as seen in the illustration. After left-right rotation is performed, we can see the arrows here. we're just going to follow it one for a clear understanding. After the proper rotation is performed, we now have a balanced tree of a root which has a root node of 20, a left child 10, and a right child 30. All of them has a balance factor of 0, making the tree balanced. Operations on AVL tree, the following operations are performed on AVL tree. So first, I'm going to discuss search operations in AVL tree. In an AVL tree, the search operation is performed with O-log in time complexity. The search operation in AVL tree is similar to the search operation in binary tree. We use the following steps to search an element in an AVL tree. So you're going to follow these steps, but for the purpose of this discussion, I'm going to explain the illustration. So we are given a key element or node we're going to find equals to 30. So first we are going to go to the root node, which is 40. Now 30 is less than 40, which means the node we are trying to find should be on the left side, because the left side is always less than the right child. So 30 is less than 40. Here we are faced with 20, but 20 is less than 30, meaning to say that the key or node we're trying to find is on the right sub-tree. So here, the same goes in finding 60. So 60 is greater than 40, which means it is on the right part of the tree. So we are faced with 50 on the next part, and 50 is less than 60, meaning to say that 60 is on the right sub-tree.
So if balance factor of any node is 0, it means that the left subtree and the right subtree contain equal height. If balance factor of any node is -1, it means that the left subtree is one level lower than the right subtree. We can see that balance factor associated with each node is in between -1 and +1. Therefore, it is an example of AVL tree. So AVL insertion process. Insertion in an AVL tree is similar to insertion in a binary search tree, but after inserting an element, you need to fix the AVL properties using the left and right rotations. So when to use rotations? If there is an imbalance in the left child's right subtree, perform the left-right rotation. Second, if there is an imbalance in the left child's left subtree, perform a right rotation. Third, if there is an imbalance in the right child's right subtree, perform a left rotation. Fourth, if there is an imbalance in the right child's left subtree, perform the right-left rotation. Let's construct AVL tree for the elements 1, 2, 3 as you can see the illustration. So inserting 1, you see the balance factor or node 1 is 0 because there is no left and right subtree. Inserting 2. Next, insert the 2 elements. So 2 is greater than 1. It should be the right subtree. You see the balance factor of 2 is 0 and the balance factor of 1 is -1. Therefore, the tree is balanced. Next, insert the 3 element. It should be inserted at the right child because 3 is greater than 2. As you can see, the balance factor of 3 is 0 and the balance factor of 2 is -1 and the balance factor of 1 is -2. We have to perform the left rotation. So as you can see, the arrow, since it is invalid to use the 1 element, the 2 will become our parent node. So the 1 become the left subtree and the 3 become the right subtree. So as you can see, the balance factor of each element is 0. Therefore, the tree is balanced.
So,
let's talk about another operation performed in AVL trees, the deletion. Deletion is also very straightforward. We delete using the same logic as in simple binary search trees. So after deletion, we restructure the tree if needed to maintain its balanced height. So after deleting an element in the tree, so if it is needed to make the tree balance, we need to restructure it and calculate the balance factor of the node to determine whether if it is balanced or not. And if it's not balanced, we can use the AVL rotation to make the tree balance. So there are steps to be performed in deletion in AVL trees. So first, find the element in the tree. Step 2, delete the node as per the binary search tree deletion. And in step 3, there are two cases are possible. In case 1, deleting from the right subtree. So let's talk about only the case 1, deleting from the right subtree. So in case 1a, if balance factor of node equals 2 and the balance factor of the left child of the node equals 1, so it makes the left imbalance, and you can perform the right rotation to make the tree balance. And in case 1b, if balance factor of the node equals 2 and the balance factor of the left child of the node equals -1, so it makes the tree it became left-right imbalance. So you can perform the left-right rotation. In case 1c, if balance factor of the node equals 2 and the balance factor of the left child of the node equals 0, so you can perform again the right rotation for the left imbalance. So let's talk about the example 3 for the given cases above. So in case 1, the tree is imbalance as balance factor of 30 equals 2. So the tree is imbalanced. You can perform a right rotation at node 20. So that the tree became balanced. So in case 1b, the tree is imbalanced as balance factor of 30 equals 1. And this is the left-right imbalance. So you can perform a left-right rotation. So in left rotation, you can at node left rotation at node 20 and right rotation at node 10, and the output of this rotation became the tree balance. In case 1c, there are 5 elements given. So like in case 1a, the tree is in left imbalance, so you can perform a right rotation at node 10. So you can disregard the 20 first and perform the right rotation of the left imbalance, the node 20, node 10, and the node 5. So after performing it, the right rotation, you can put the 20 as the left child of the node 20. So the tree will become balanced as the balance factor of
30 equals -1. So that's all for the deletion in AVL trees.
So when it comes to the implementation, we are using the insertion code for the sample. So this is a Java program for insertion in AVL3. So after creating the class AVL3, which is the class that we're going to use for the main method. So here we have created a class node, and then inside the class AVL3 we can see a utility function to get the height of the tree. Next part is a utility function to get maximum of 2 integers. Now on this part we can see a utility function to rotate the right subtree rooted with y here. The next is a utility function to left rotate subtree with rooted x. Next is to get balance factor of node n, and followed by the node insert, which has a function to perform the normal binary search tree insertion. So this is the update height of this ancestor node, and we're going to get the balance factor of this ancestor node to check whether this node became unbalanced. So in this part, this node becomes unbalanced. Then the right case here, left right case, right left case is here, and we're going to return node. So next is we're going to put the utility function to print pre-order traversals of the tree. So this is a pre-order. The function also prints height of every node here. So next is the main method that prints the tree given in the above figure. This is supposed to be an illustration of the constructed AVL tree. So if we're going to run this is the program, or this is the output. So 30, 20, 10, we were going to start with the left, and then 25, next is 40, and 50. So for guided practice, we have a general instruction to write your answer on a piece of paper, scan the document, take a picture of the documentation, and send as PDF to Google Classroom. So first, we have insertion. So after inserting 7, the AVL tree becomes imbalanced. Draw and balance the AVL tree using the appropriate rotations as stated in the presentation. Don't forget to write the rotations used. So we're going to insert 7 here, insert 6. So the student will write the appropriate rotations and draw, also balance the AVL tree. So next is the deletion part. So delete the node on the AVL tree and draw the AVL tree after its deletion, showing a balanced AVL tree. So if it is not a balanced tree, use the proper rotation to get the answer. For CompuSkills performance tasks, create your own 5 balanced AVL trees, 3 of which are already balanced and the remaining 2 are unbalanced AVL trees, which shows the appropriate rotations needed in order to make 5 balanced trees. So don't forget to scan the document, take a picture of the document, and send as PDF to G Classroom.